Hey class, this is going to be a short video on a topic called Library of Parent Functions. What this section is going to be all about is getting you familiarized with some of the functions that we're going to be working with in the upcoming weeks. We're going to be moving into a topic called transforming parent functions, so we have to introduce what those parent functions look like. You're going to have to be able to identify what their equations look like as well as what their graphs look like. So just keep that in mind. There may be a lot of information coming at you in a short amount of time. You're not required to memorize all of the facts, although that might help you. You really just want to think about this as playing flashcards in your brain. Can I identify what the function is, the function type, and what its graph should look like? Okay. So first, we're going to outline some of the common parent functions, polynomial functions, radical functions, and then a few others that you may see in the ALEKS homework. And then we'll play a game called Name That Function and just kind of look at some examples just to make sure that we have some practice. So first, the phrase parent function refers to the simplest form of a whole family of related functions. So um, these functions could be a little bit different in the same way that, if you are a member of a family, your family members look similar to you, but not exactly the same. Okay. There are many functions that we're going to graph in this section, so you just need to be prepared to identify which graph corresponds to which equation, or another way of putting it is, what is the name of this type of function when you see a picture of it? Okay. So we'll first start off by introducing the polynomial functions, and some of these may be familiar to you already. For instance, your polynomial functions are going to be defined by polynomial expressions. What does that mean? Well, remember that a polynomial is just an algebraic expression that is made up of variables and constant terms, but all of the variable terms have to have a non-negative integer exponent. That means that if you have like x with an exponent on it, that exponent has to be 0, 1, 2, 3, and so on. They can't be fractions. They cannot be negative numbers. Okay. A polynomial is characterized by its degree. And the highest exponent that you see in a polynomial function, that number represents the degree of the polynomial. The most common polynomial functions that we'll see in this class are linear functions, quadratic functions, cubic functions. Okay, so let's start off with linear functions. You guys are used to seeing this as f of x is equal to mx plus b, but just to see a pattern emerge, I like to put it as f of x equals ax plus b. Okay, so if you just turn your attention to the variable right here, this variable term, the x part of that variable term has an exponent. We don't see it, so we understand that that has an exponent of 1. Okay, so a linear function represents a first degree polynomial function precisely because the exponent on the variable x is a 1. Okay, now you might be thinking to yourself, the a and the b, aren't they variables as well? Well, depending on the problem that we're going to be given, A and B are just going to be some random numbers, okay? And they'll change from problem to problem, but what will stay the same across all linear functions is that x will have an exponent of 1, okay? So the parameters A and B, as you probably have learned this in a previous math class, A represents the slope of the function and B represents the y-intercept. So where the line graph crosses the y-axis. All linear functions are going to represent straight lines, so they're not going to be curved. There's not going to be any bends or any pointy sort of angles to the graphs. Okay, so anytime you see a perfectly straight line, it can be very steep. It could be kind of shallow or not very steep at all. That's going to be a linear function. Okay. Okay. Our first type of linear function is called a constant function. A constant function is a linear function that has a slope of 0. So if we back up just a little bit, that means that this term right here, if that is a 0, then f of x is just equal to b, which is just going to be some number. Okay. All right. What does that mean and how does it impact the function? Well, because the slope is zero, if you think about something that doesn't have a slope at all, like an object in real life, if you're trying to climb up a hill or walking down a road, if it has zero slope, that means it's neither inclined up nor inclined down. It's perfectly flat. So constant functions will always appear to be perfectly horizontal lines, and they'll be parallel with the x-axis, again, because the x-axis is that horizontal line on our Cartesian coordinate system, okay? The equation for a constant function is going to be f of x is equal to b, where b is just going to be some number. Whatever that number is represents both the y-intercept and the level or the height of that perfectly flat horizontal line. So, for instance, if we were to say we have a function f of x is equal to, and let me just replace this b with the number 2, then we can expect for us to have a y-intercept of 2, but then also to have a perfectly flat line that goes horizontally across that y value and stays perfectly flat, doesn't curve, doesn't angle upwards or anything. Okay? Okay. So we know that b can be any number depending on the problem. And so that means that when we look at the table or try to generate a table of xy pairs, if you think about a function as a machine where you give it input values, you give it x values, we could type in like f of x where we input, let's say, -2, for instance. Then if this part of the equation, the right-hand side of the equation, uh, just has the number b, whatever that happens to be, then that means there's not a variable x next to the b, right? So that means that we cannot plug in a variable value. So even if I try to plug -2 into this function, because I don't have an x next to that value b, that means that I can't plug anything in. So the output of the function is always going to be whatever that number is. Okay. Okay. So a constant function is called constant is because the output never changes. It remains constant. It's going to be whatever that value is. Okay. Now that's going to be different from our next linear function, which is the identity function. And the identity function is usually thought of as the parent function for all linear functions. The identity function is a perfectly diagonal line that crosses through the origin, and we can say that it has a slope of 1. Okay. Um, the identity function is interesting because any input, any x value that you plug into this function, well, that's going to be the same thing as the output. So here, our y value will just be whatever x value we give to this function. Okay, so if we plug in a -2 into f of x, then the output is just x, which is that same value that we gave it. So we'll output -2. Similarly, if I just picked a random number like 5 or 8, if I plugged 8 into this function, then the output would also be 8 because you can think of this identity function, that name, as indicating that whatever you put into the function returns the identity of that value, or sort of like looking in the mirror, the function will just return the same thing that you gave it. Okay. That might seem like a lot of information right now, but remember, linear functions are just going to be perfectly straight lines, and that is how we need to think about this right now. Okay. Next, we'll talk about quadratic functions, which is kind of a level up from the linear functions. And what I mean by that is that a basic quadratic function has an x variable term where the exponent on x, the highest exponent, is a 2. So quadratic functions are second-degree polynomial functions. They can easily be identified because the leading term has a squared variable. Okay. And the output, the graph of these functions, end up being what we call a parabola or a U-shaped graph. Okay. First quadratic function that we need to think about is the squaring function, which is the parent of all quadratic functions. And we can see that we have a perfectly U-shaped graph over there on the right-hand side. The equation for the squaring function is f of x is equal to x squared. Okay, so anytime you see a graph or a polynomial expression that has x squared as the highest degree term, that is the exponent is 2, then you can expect some sort of U-shaped graph. Okay. The reason why this one is called the squaring function is because if we think about the input value here, the -2, and plug it into the equation or plug it into the function, then that means we would write -2 and then square it. Well, since squaring means multiplying it by itself, -2 times -2 will end up being +4, which is what we see here in the table. Okay, so this is called the squaring function because the function will take the input and then square it, multiply it by itself, and then that's going to be your y value. Okay. All right. So for quadratic functions or the squaring function, we should expect a U-shaped graph. Okay. The next kind of polynomial function is a third degree polynomial function. We call these cubics. Okay. And some of you guys might be familiar with the term cube. When you raise something to the third power, we say that it is cubed. Okay. This kind of function is a wiggly function. It kind of wiggles up through the origin of the graph, so through that 0, 0 point in the middle, and then kind of curves upwards again. Okay, kind of like a S-shaped curve a little bit. Cubics can easily be identified by finding that third power term, that x to the third power. And I like to describe these as wiggly graphs, but they're upright wiggly, not turn to the side wiggly, upright. Okay. Radical functions are another type of function that we're going to be sort of playing around with in the next couple of sections. Our first radical function is a square root function. So if I use the square root in the calculator, I can generate some values, some y values, and it will always produce a graph. When we take those xy pairs, it will always produce a graph that's kind of this arc shape. So the equation for this function will be f of x is equal to x, the square root of x. Okay. And this function only takes non-negative input values. Okay. You may have learned about taking the square root of negative numbers, giving you imaginary numbers. Okay, and we're not talking about imaginary numbers just this minute. So whenever we have an input in a square root function that is negative, then we need to select the option that says our output is not a real number. Okay. However, if you can't take the square root of a number, then the output is going to be whatever that square root is. So for instance, let's say for a moment that I wanted to say x is equal to 25 here and plug that into our function. So if x is equal to 25, I can plug 25 into my function, and then that means I need to take the square root of 25. Okay. Now, some of you, depending on your skill level and what you remember from your previous math classes, might know off the top of your head what the square root of 25 is. But if you're not sure, you could throw that in the calculator, and the calculator will tell you that the square root of 25 is 5. So here we have our x value, and now we have a y value, and we can plot those coordinates accordingly. Okay. But again, all we need to know for this moment is that a square root function, f of x equals the square root of x, will generate this arc shape. Okay. Okay. The cube root function is similar to the square root function, except it has a little bit more going on in the graph. Okay. The cube root function is given by the equation f of x is equal to the cube root of x. We will have a whole section later on about radicals and roots, but when you see this little number here next to what looks like the square root symbol, This is a new kind of root, okay, that you may or may not be aware of, but there are many kinds of roots. The cube root is the third root. If I had a number 4 here, that would be the fourth root. A number 5 there, that would be the fifth root. And that's a topic that we'll get to a little bit later on. Okay, but for now, if I see a 3 next to the root symbol, you need to remember that's the third root or the cube root function. Okay. Now, this function can take both positive and negative numbers. And so we can see the domain of this graph that we have over here on the right does take negative numbers. So the domain over here does extend into the negative side of our number line. Okay. But it also extends all the way to the positive part of our domain, or the positive part of that x-axis. Okay. And this is the function where, kind of similar to the cubic function, where you had a squiggly function that's going upright, the cube root function is a squiggly function that goes kind of like tilted on its side, kind of squiggles horizontally. Okay. So there are some XY values that you see there. And if you want to, just as an exercise for yourself, you can go ahead and try to plug these X values into the function. If you can find out how to use the cube root function in your calculator, go ahead and put the cube root of 0 in there. And it'll look like this, cube root of 0. And when you hit enter, you should get an output of 0. But go ahead and try that for each of these X values. Try to find the cube root on your calculator, and you'll see that the output should be what we have here for our Y column. Okay. Okay. There's a couple of other common functions that we're going to play with in the next section. For instance, the absolute value function is this V-shaped function that kind of looks like two linear functions that kind of meet at the origin at that point at the bottom of the V. Okay. The absolute value function looks like f of x is equal to, and then we put these absolute value bars, these vertical bars around the x. So whenever you see these vertical bars, that indicates the absolute value of x. Now, the absolute value of x means that you're trying to find the distance that that number is from 0 on the number line. And if you think about distances in real life, like if you pulled out a measuring tape and tried to measure how long something is or how far away an object is from you, the measurements on a measuring tape are always positive. It doesn't matter if I'm measuring something that's, to the left of me or to the right of me. Whenever I report that distance, it's going to be a positive number. So if I take the absolute value, for instance, if I take the absolute value of a negative number, like the absolute value of -2, okay, this is like asking how far from 0 is -2 on the number line. So what is this distance here? Okay, and again, we only measure distance in positive units. So if I'm trying to measure out from 0 all the way to -2, then that has a distance of 2, +2, right? And we can see that our graph represents that point right here, where we have our ordered pair at -2, comma 2. Okay, and that point is right here on our absolute value function. Okay. So again, if I needed to find the absolute value of +2, I could plug this into my function right there. And then I can say to myself, okay, well, I'm looking for the absolute value of +2. And that's like asking how far is 2 away from 0 on the number line. Well, that's just 2 units. So that's going to be a Y value of 2 as well. So if I look at this ordered pair that I have, 2, comma 2, then I should be able to go over to the right 2 and then up 2, and I definitely have that point on my function. So the absolute value function is always going to give you this V-shaped function. Okay, don't confuse that with the quadratic function, which is a U-shaped function. It has a curve. The absolute value function is always going to be pointy. Okay. Then later on, we're going to get into what are called rational functions. The reciprocal function is the first one of that type. Okay. And those are represented by fractions where we have the variable x in the denominator of the fraction. Okay, so if we have a variable in the bottom of a fraction, then that's going to represent a rational function. And the reciprocal function is just the function 1 over x. It's the simplest form or the parent of all rational functions. Okay. These graphs that are produced by rational functions look a little bit weird. What I mean by that is that it's broken up into multiple parts. And again, when we get to this topic later, we're going to understand why is there a gap right here, seemingly in the middle of these two parts of the graph. Okay. But what you should be thinking to yourself is if you see a graph that has multiple parts and they kind of look like they're curving away from each other and they're leaving a gap or a space in between them, then you should automatically think that the parent function is a reciprocal function. Okay. Okay. So I know that was a lot thrown at you. We're going to play around with that idea a little bit more. So right now, I just want to make sure that we can, test ourselves, test our skills on identifying what type of function these graphs come from. So for the next few slides, I'm going to present you with some graphs that are transformed. So they look a little bit different from the parent functions, but you need to tell me what parent function do these graphs come from. Okay, if we look at this first graph, we might ask ourselves, well, what is the general shape of this graph? Is it a line? Is it a U-shaped graph? Is it a V-shaped graph? Is it one of these graphs that has multiple parts? Well, if this is a perfectly straight line, then we need to recognize that this is a linear function. So the identity function f of x equals x, that is the parent of this function. Okay, because it's a perfectly straight line, linear function. That's how you should relate those in your mind. The next one, we can take a look at these two functions, two parts of the same function, really. And we can notice that we do have kind of a gap running between those two parts. Okay, so the graph doesn't seem to be intersecting each other. They're not connected. And since we have this gap in the middle, you should be thinking to yourself, oh, this is a rational function, and its parent should be what function? Well, that's the last function that we looked at, the reciprocal function, 1 over x. Okay, so if I have any graph that looks like that, that's broken up into multiple parts, and it kind of looks like swirly, like a vortex with that gap in the middle, then that's going to be a reciprocal function, or it comes from a reciprocal function. What about this one? Is this a linear function? Is it quadratic? Is it cubic? Okay. Remember, linear functions are perfectly straight lines. Cubics are U-shaped graphs. Sorry, quadratics are U-shaped. Parabolas. Cubics are squiggly. Square root function is the arc. The cube root function is the sort of squiggle on its side. And then the absolute value function is the one that's shaped like a V. Okay. So this one is kind of turned upside down, but if we still have that V shape, it doesn't matter if that's upside down or right side up. That's still going to come from an absolute value function. Okay. Okay. Now, this graph is kind of windy, okay, kind of squiggly. So you might right away think, well, it could be the cubic or it could be the cube root function because those are two of our squiggly functions. But if you think about this, this is squiggling kind of up and not squiggling on its side. Remember, squiggling on its side looks more like this. Okay. So if it's an upright squiggle, it doesn't matter how curvy it is. If it's going up and not out to the side, then that should be a cubic function. Okay. Okay. And we'll leave it at this one. This is the last one, function number 5. Now, this kind of doesn't look like a linear function because it has a curve to it. It's not a perfect U shape. Remember, the U shape would be a quadratic function. The cubic is squiggling up. The square root is an arch shape. And we're used to seeing that kind of right side up, where we have something starting in the origin and then going out to the right like that, like an arch. Okay. And even though this doesn't immediately look like that, well, it kind of looks like that arch shape, but we sort of turn it upside down. Okay. So even if it's upside down, it's still a family member of the square root function. Okay. So that's going to come from our square root function. Okay. So that might have been kind of a crash course in these parent functions. We're going to start working with these parent functions and sort of familiarizing ourselves with some of the basic ones when we come back to class. And we will start actually doing some mathematical manipulations to change the graph's characteristics. We can change whether they're kind of just the original parent function, whether it's a little bit taller, a little bit wider, and we can shift them around the Cartesian coordinate system as we please. We can even flip them upside down or flip them sideways. Okay, and there's some basic mathematical rules that we'll use to do that. But you have to think about being able to identify just by looking at the graph what is the type of function that you're looking at. Okay, and if you can do that, then that's going to be half the battle. Okay, so we'll bring it all together in class, and hopefully this is helpful. So I will see you